Chapter 1, Section 1. What is science? One ancient evening, lost in the mist of time, someone looked into the sky and wondered for the first time, what are those lights? Where did the plants and animals come from? How did I come to be? Since then, humans have tried to answer those questions. At first, the answers our ancestors came up with involved tales of magic or legends like the one that accounted for the eye-like markings on the peacock tail in Figure 1-1. Then, slowly, humans began to explore the natural world using a scientific approach. What science is and is not. What does it mean to say that an approach to a problem is scientific? The goal of science is to investigate and understand the natural world, to explain events in the natural world, and to use those explanations to make useful predictions. Science has several features that make it different from other human endeavors. First, science deals only with the natural world. Second, scientists collect and organize information in a careful, orderly way, looking for patterns and connections between events. Third, scientists propose explanations that can be tested by examining evidence. In other words, science is an organized way of using evidence to learn about the natural world. The word science also refers to the body of knowledge that scientists have built up after years of using this process. Thinking like a scientist. Suppose a car won't start. Is the car out of gas? A glance at the fuel gauge tests that idea. Perhaps the battery is dead. An auto mechanic can use an instrument to test that idea. To figure out what is wrong with the car, people perform tests and observe the results of those tests. This familiar activity uses the approach scientists take in research. Scientific thinking usually begins with observation, the process of gathering information about events or processes in a careful, orderly way. Observations generally involve using the senses, particularly sight and hearing. The information gathered from observations is called data. There are two main categories of data. Quantitative data are expressed as numbers, obtained by counting or measuring. The researcher in Figure 1-2, for example, might note that the manatee has one scar on its back. Qualitative data are descriptive and involve characteristics that can't usually be counted. The researcher might make the qualitative observation that the scar appears old and the animal seems healthy and alert. Scientists may use data to make inferences. An inference is a logical interpretation based on prior knowledge or experience. The researcher in Figure 1-3, for example, is testing water in a reservoir. Because she cannot test all the water, she collects water samples from several different parts of the reservoir. If all the samples are clean, enough to drink, she may infer that all the water is safe to drink. Pay attention to Figure 1-1. Male peacocks have markings on their tails that resemble giant eyes. According to an ancient Greek myth, the peacock's eyes once belonged to Argus, a giant with 100 eyes. An angry goddess had Argus killed, but she transferred the giant eyes to the tail of the peacock. Now look at figure 1-2. The goal of science is to investigate and understand nature. The first step in this process is making observations. This researcher is observing the behavior of a manatee in Florida. Look at figure 1-3. Researchers testing water for lead pollution cannot test every drop, so they check small amounts called samples. Explaining and interpreting evidence. Scientists try to explain events in the natural world by interpreting evidence logically and analytically. Suppose, for example, that many people contract an unknown disease after attending a public event. Public health researchers will use scientific methods to try to determine how those people became ill. After initial observations, the researchers will propose one or more hypotheses. A hypothesis is a proposed scientific explanation for a set of observations. Scientists generate hypotheses using prior knowledge or what they already know, logical inferences, and informed creative imagination. For the unknown disease, there might be several competing hypotheses, such as these. 1. The disease was spread from person to person by contact. 2. The disease was spread through insect bites. 3. The disease was spread through air, water, or food. Scientific hypotheses must be proposed in a way that enables them to be tested. Some hypotheses are tested by performing controlled experiments. As you will learn in the next section, other hypotheses are tested by gathering more data. In the case of the mystery illness, data would be collected by studying the location of the event, by examining air, water, and food people were exposed to, and by questioning people about their actions before falling ill. Some hypotheses would be ruled out, others might be supported and eventually confirmed. Researchers working on complex questions often collaborate in teams like the one in figure 1-4. These groups have regular meetings at which they analyze, review, and critique each other's data and hypotheses. This review process helps to ensure that their conclusions are valid. To be valid, a conclusion must be based on logical interpretation of reliable data. To learn about sources of error in scientific investigations, see Appendix A. Now look at figure 1-4. Researchers often collaborate by working in teams, combining imagination and logic to develop and test hypotheses. Science as a way of knowing. This book contains lots of facts, but don't think biological science is a set of truths that never change. Instead, science is a way of knowing. This means that rather than unchanging knowledge, science is an ongoing process, a process that involves asking questions, observing, making inferences, and testing hypotheses. You can learn more about these and other science skills in Appendix A. Because of new tools, techniques, and discoveries, such as the discovery shown in figure 1-5, scientific understanding is always changing. Research can have a profound impact on scientific thought. For example, the discovery of cells revolutionized understanding of the structure of living things. Without a doubt, some things you learn from this book will soon be revised because of new information. But this doesn't mean that science has failed. On the contrary, it means that science continues to succeed in advancing understanding. Good scientists are skeptics, which means that they question both existing ideas and new hypotheses. Scientists continually evaluate the strengths and weaknesses of hypotheses. Scientists must be open-minded and consider new hypotheses if data demands it. And despite the power of science, it has definite limits. For example, science cannot help you decide whether a painting is beautiful or whether school sports teams should be limited to only the best athletes. The scientific way of knowing includes the view that the whole physical universe is a system, or a collection of parts and processes that interact. In the universe, basic natural laws govern all events and objects, large or small. The physical universe consists of many smaller systems. Biologists focus on living systems, which range from invisibly small to the size of our entire planet. Take a look at Figure 1-5. In 1991, hikers in the Italian Alps discovered a well-preserved corpse that was about 5,000 years old. Scientists might have asked how the corpse could be so well preserved, but they already knew the answer. Sub-zero temperatures keep the organisms that cause decomposition from doing their job. Science and human values. Because of new knowledge gained through research, scientists continually revise and reevaluate their ideas. The importance of science, however, reaches far beyond the scientific world. Today, scientists contribute information to discussions about health and disease and about the relationships between human beings and the living and non-living environment. Make a list of things that you need to understand to protect your life and the lives of others close to you. Chances are that your list will include drugs and alcohol, smoking and lung disease, AIDS, cancer, and heart disease. Other questions focus on public health and the environment. How can we best use antibiotics to make sure that those wonder drugs keep working for us a long time? How much of the information in your genes should you be able to keep private? Should communities produce electricity using fossil fuels, nuclear power, or hydroelectric dams? How should chemical waste be disposed of? Who should be responsible for their disposal? All these questions evolved scientific information. For that reason, an understanding of science and the scientific approach is essential to making intelligent decisions about them. None of these questions, however, can be answered by science alone. They involve the society in which we live and the economy that provides jobs, food, and shelter. They may require us to consider laws and moral principles. In our society, scientists alone do not make final decisions. They make recommendations. Who makes the decisions? We, the citizens of our democracy, do. When we vote to express our opinions, to elect officials. That is why it is more important than ever that everyone understand what science is, what it can do, and what it cannot do. Look at Figure 1.6. Scientific research has an impact on many aspects of our lives. These racers are raising money to help support research directed at preventing and treating cancer. In your notes of this chapter, identify 3 ways in which science affects your life.